Now, here one thing is that as compared to outside the solenoid, outside here, just outside, and then just end. If you compare this, this magnetic field is quite strong as compared to this. If it is a very long solenoid, then the outside field is 0 and inside field is mu naught Ni parallel, but once it reaches the end, it has to diverge and then close. These are all closed lines. So, here if you see, the magnetic field is small and here the magnetic field is large, but more than that, remember, if you have a pin or a small thing and you place it in a uniform magnetic field, however strong, very strong magnetic field, but uniform, and then I place my material here. This is say just an alpine or some iron nail or something. So, this magnetic field will magnetize this iron nail, and if this whole thing is uniform, if this magnetic field is all uniform, then hopefully this nail will also get uniform magnetization, and then the magnetic field will not exert any force on this nail, however strong the field be, right. Because if you have a dipole, you know, the net force on the dipole, net magnetic force on the dipole is 0 if the magnetic field is uniform. So, variation in magnetic field is important, or in our that magnetic charge model, I can say that all right, here it is minus qm and here it is plus qm, and if the field is same, then the two forces are same in magnitude, opposite in direction. So, variation is needed, and here is the variation. And here is the variation. So, if you bring a pin here or nail here, it will be attracted, but if you place it here, you will find that almost no force is there, right. So, but inside the magnet, if you go inside the magnet, the field is strongest here and it becomes weak here. So, that is the kind of thing. Now, the end from where the field lines are coming out, this end is known as north pole, people call it north pole, and the other end where the field lines are entering, that is known as south pole. And people talk of similar poles and dissimilar poles, attract, repel, etc., etc. Now you know that there is nothing like poles. Your magnet is here, your magnet is here, your currents are this. So, this current here, last, this loop here, this loop here, this loop here, and this loop here, they are all identical. They are all identical. If it is anticlockwise here, it is anticlockwise here. If it is clockwise here, it is clockwise here. Not only the two ends, even the middle. This current loop is also same as this current loop. So, there is nothing special here which you call south pole, or nothing special here which you call north pole. It is all anticlockwise or clockwise currents, identical structure, only shifted. The loop is here, you shift it, you will get this loop, you shift it, you get this loop. No change, no material change, is the same loop. But then how do we say that the two north poles, if they are coming close to each other, then they will repel, and if south pole comes there, then it attracts, as if in electrostatics we do say that, yes, the positive charge and the negative charge are two different entities, and then positive charges repel, negative charges repel, positive negative charges attract. But here they are not two different entities. You do not have two kinds. In electric case, yes, you have two kinds of these charges, but which create this magnetic field, but this electric field. But here these are the current loops, and the current loops are all identical here to here. Magnetization all identical, the magnetization here, the magnetization here, the magnetization here, the magnetization here, magnetization here, everything here and here and here and here are identical, but still it appears as if there are two kinds of poles, and similar poles repel and dissimilar poles attract. So, we can understand it that attraction repulsion on the basis of what we have discussed, and let me take our magnets like this. Suppose this is a material, this is a magnetized material, the magnetization is in the z direction, and if the magnetization is z direction, the surface current will be in phi cap direction. So, the currents will be like this. I am just trying to draw the current. So, here the current will be like this, here the current will be like this. Can you see the arrow, this arrow here and this arrow here? So, the current is like this, m cross n cap, essentially m cross n cap. The current is like this, and so on. You can do it. You can do it for the entire mango, and let me quickly do it here and then come here near the end, all right. So, if this is the current, the magnetic field will be, the field lines will come from this side. So, this is that so called north pole, this is the so called north pole, and this is the so called south pole. Let me take another magnet, and we do the same thing here, same identical magnet, identically magnetized. So, the currents will be like this. This is the arrow, this is the arrow, this is the arrow. This is the arrow, and this is that arrow at the last one, and the magnetic field is coming here and going here. So, this people will say that this is north pole, this is north pole, and this is south pole. Okay. Now, let me bring these two magnets which are identical. You can see that. You can see that it is all identical, north pole here, north pole here, the arrows are like that, similar arrows on the two magnets. And suppose I put it here, I put it here. So, here is that N, north pole of this, and here is the S. But think in terms of currents. What are the currents? On this mango, this is the current is going like this, see the arrow, it is going like this, on this it is going like this. The currents are parallel, the currents are parallel, and you know that parallel currents attract, therefore it is attracting. It is not there are dissimilar poles, something different kind of thing here and different kind of thing here, they are dissimilar, they are not dissimilar, they are similar. And similar in the sense here you have current and identically same current is here, same current, same direction, and therefore this current and this current, they are parallel to each other, and parallel currents attract. That is why this N and this S, they attract. If I put it here, the same story. If I put it here, the same story once again. This current and this current are same, this current going this way, this current going this way. So, parallel currents will attract anyway. Here also, see this is also that same in the same direction, this one. So, this one is also attracting this. Not only this is attracting this is also attracting this. because here also you have parallel currents. So, not only that north is attracting south, the south is also attracting south. Okay. So, there is an overall attraction, but if I invert one of them, see what happens now, right. So, it was like this and I have inverted this. So, this N goes here and S goes here, this N is here and this S is here. Now, look at the arrows, here the current is going like this and here the current is going like this, here the current is going like this and here the current is going like this. They are anti-parallel currents. If you call the similar sense of current as similar, and anti-parallel, if it is, you say that they are opposite to each other, they are anti-parallel currents, and because of this dissimilarity, because of this anti-parallel, these are repelling each other. So, not the similar ones are repelling, the dissimilar ones are repelling. And remember, here also, this end also, the current is this way on this magnet and current is this way on this magnet. It is being repelled by not only this current, but also by this current. But overall, when you just look at it from outside, you say that okay, fine, this is N and therefore they are repelling. And if I have inverted it here, you will say that okay, you have brought S here, N here, and therefore they are attracting. So, this mechanism of attraction repulsion is very interesting of magnets, and if you understand that, then you will enjoy more.